compounds.
Good morning. It's 12:33 on the 6th of December. It's good to stare into a screen and by extension, stare at you. That came out weird. It's Wednesday the 6th. You guys are about to learn about synthesis reaction and decomposition reaction. This is for Mrs. Wathen and Mr. Chancer's kids, and for anybody who watches this. Cool. This is my second take, and it's late, but we're going to get through this. So here we go. A chemical reaction, a synthesis chemical reaction, is a chemical reaction in which two or more substances react to create a single thing. All right. So if we think about what's going on here, all right, we have, say, element A and element B, which gives you a molecule consisting of elements A and B. All right. But it isn't exclusive to single elements, right? Like we can have entire molecules that become a larger molecule. That's just so synthesizing is just coming together, creating something. All right, the examples below, all right, we have 3 magnesium atoms combining with diatomic nitrogen to give us magnesium nitride, right? And the same thing is happening over here where we have two pre-existing compounds, calcium oxide and water, okay, on the reactant side, giving us the products of calcium hydroxide. Okay, and another byproduct of that is going to be heat, right? Which is obviously not an element, all right? We would just write that, okay? All right, so some important things to note when you're writing synthesis reactions, all right? First, write the cation. Second, write the anion, the negatively charged, okay, element or compound, okay? The subscripts from the reactants, we don't carry them over, so we are going to add subscripts to the reactants, all right, in order to make sure that those are neutral or appropriately set up. But on the product side, and actually let me kind of switch my hands, so reactants are over here, right? On the product side, we're not going to carry those over. We are going to let coefficients do the work, okay, on the product side for balancing the equations, right? We will be swapping and dropping. That's what we're talking about when we refer to subscripts. It is super important that we refer to the states of matter, okay, being liquid or solid or gaseous, or at least probably not today. I don't think we'll see any aqueous, but that just means that we have, okay, it's a solution. It is elements that are being dissolved or contained within like water, right? So it's not water. That's why we don't call it water, all right? But it's aqueous. It's a solution, all right? And then finally, and most importantly, all right, the reason why we're doing all of this is we have to balance these equations, okay? All right, so let's start with this example. We have magnesium reacting with oxygen in the air. All right, okay, I think we got it. So we know we have Mg, try and make my writing a little neater this time. And then we know we're gonna have a plus sign because that magnesium is gonna mix with the oxygen. And then the important thing to know about the oxygen is it's a diatomic molecule. So you're gonna have an O2, all right? The other thing that we talked about is making sure we add physical states, okay, to our chemical equations, all right? And this is a synthesis reaction, so it's going to synthesize, okay, into magnesium oxide, okay? And we're going to put the physical state that it's a solid. Notice we do not carry the subscripts. We don't do that, all right? All right, we are not going to do that, but we are going to return to our faithful friend, the minnow, okay? So just to make sure that we're following the correct order of operations, for lack of a better phrase. So magnesium is a metal, all right, so we're going to list the magnesium. Okay, we're going to put that as a solid. We're going to basically recreate the skeleton equation down here and begin balancing. Okay, so I'm going to put my line of demarcation between the reactants and the products. Magnesium, we have 1. Oxygen being a diatomic molecule, we have 2. Okay, magnesium, we have 1 on the product side, and then oxygen, we have 1. And this egregious line was meant to be an S for solid. All right, so let's focus on the odd, okay, oxygen. Notice that our metals are balanced. Notice that we do not have any polyatomic ions. We have no nonmetals that are not oxygen. So we're going to focus on the oxygen. We're going to focus on the odd oxygen specifically, because making an odd and even makes things, aka balancing equations, generally easier to deal with. So that's what we will do. All right, because we put a coefficient of 2 in front of the magnesium oxide, we now have 2 magnesiums, okay? And look at me, it's late. I can't even complete the elemental symbol. There it is, magnesium and oxygen, 2 and 2. That brings us back to the reactant side, where we need to make sure that this magnesium has a 2. Okay, and we have 2. Okay, the reactant side, 2 magnesiums, 2 oxygens. The product side, 2 magnesiums, 2 oxygens. That's not balanced, ladies and gentlemen. Let's keep going. All right. Okay, I'm going to put our faithful acronym up there to use. All right, remember we are doing synthesis reactions. We are not going to carry the subscripts. We're going to go ahead with the reactant side and put the physical states. All right, we have strontium, which is a solid. We have diatomic oxygen, which is a gas. And since they are synthesizing, they are going to combine. We are not going to carry, all right, that subscript over. Okay, we have 1 strontium, 2 oxygens, 1 strontium, 1 oxygen. All right, we're also going to assume this to be a solid right now. Okay, we need to take this oxygen and we need to effectively make it an even number. We're going to do that by putting a coefficient of 2 in front of strontium oxide. That's going to give us both 2 oxygens and 2 strontiums. Okay. On the reactant side, we're going to add a 2 in front of that strontium. All right, so we have 2 strontiums. Okay, we have a diatomic oxygen giving us 2 oxygens, and then because of the coefficient, we have 2 strontiums and 2 oxygens in strontium oxide. Pardon me. There it is. Okay, that is balanced. Moving on, we have sodium, which is a solid, and as you already know, oxygen is a gas. It is a synthesized chemical reaction. Synthesized chemical reaction. So that's going to be, okay, what am I writing? Okay, it's going to be NaO. Right? Do not carry the subscripts. Okay. Na, one of them. All right, that's the metal. We're going to focus on metals. No polyatomic ions. We have no nonmetals that are not oxygen, so we'll move to the oxygens. We have 2. Okay, over here we have on the product side 1 sodium and 1 oxygen. We need 2 oxygens. All right. That gives us 2 sodiums and 2 oxygens on the product side. We need to go back and adjust the coefficients on the reactant side. So we have 2 sodiums, okay? And we already have 2 oxygens, so now this is effectively balanced. All right, if at any point in time, like you get lost, you miss a step, okay, pause the video, go backward, okay, review carefully what we're doing here. I'm moving a little bit quick, but all right, these are pretty straightforward, and it should make sense at this point. Let's keep going. All right, we're going to do potassium and chlorine, okay, so we know we have a K. We know we're going to have this. We know chlorine is a diatomic molecule. Okay, we know potassium is going to be a metal and a solid. We know that chlorine is going to be a gas. All right, and we know that it is going to become KCl. Okay. One of the things we need to consider here is we have a -2 charge. Okay. Potassium is, and I'm going to verify, is it group 1 or 2? Let me, okay, it's super late. I'm just going to make sure I'm setting my equation up correctly. There it is, group 1. For the love of Pete, could not remember. Okay, we're going to keep these wonderful annotations that I'm making. Back to the presentation as schedules. Scheduled? I'm English now. Okay, so because this is a 1, okay, a +1, we are going to, in fact, okay, need 2 of them. All right, so my suspicions were valid. Okay, and I'm actually going to go back and clean this up just a little bit. I'm going to do that just for your viewing. Okay, pleasure. There we go. That looks a little bit better. All right. So this one's really easy to balance. Okay, and what I mean by that is you can see clearly. All right, we have 2 potassiums. Okay, and we have 2 chlorines. All right. We have 1 over here. Okay, 1 potassium and 1 chlorine. So we're going to go ahead and we're not going to skip any steps. We're not going to take any shortcuts. All right, we're going to focus on the metals. There's, okay, and apparently I'm just rushing. There's 2 potassiums, 2 chlorines, and on this side we have 1 potassium and 1 chlorine. Okay, we need to go ahead and put a coefficient of 2 up here, and that will effectively balance, okay, this synthesized reaction of potassium chloride. All right, so hopefully that makes sense. I want you guys to go ahead and attack this one. All right, be mindful on the reactant side with calcium and fluorine, okay, of their respective charges. All right, so you can put a subscript on the reactant side, but don't put it on the product side. That's what the coefficients are for. All right, go ahead and give that one a shot. All right, and then I want you to look up, okay, the result to make sure you've got that correct. Okay. All right, moving on to decomposition reactions. A decomposition reaction is a reaction in which a single compound, okay, a single compound, a molecule breaks down into its two, okay, individual, okay, parts, or its two constituent parts. So if you have element A and element B, and it breaks down into, okay, elements A and B separately, that's a decomposition reaction. All right, they do require energy. All right, so if we think about this molecule, the imaginary molecule A and B, AB, right, it's going to take heat, okay, or light or electricity. It's going to take energy to get in between, okay, the molecule down to the bonds and to break those bonds apart. All right, so they require energy such as heat, light, or electricity. Okay, so in this example reaction that you've been given, okay, we have sodium trinitride, okay, breaks down into two sodium atoms and 3 diatomic nitrogens. All right, notice we kept the physical states. All right, so that's good. All right, when writing decomposition reactions, the things we absolutely have to kind of keep in our mind's eye. Now, the diatomic elements, okay, bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. All right, those are super important to remember as diatomic elements. We also need to wow, language is escaping me at this hour. Okay, metal hydroxides, okay, meaning metal with hydroxide, okay, are going to break down into metal oxides and H2O. That's what we mean by water, obviously. All right. We do need to make sure we are writing down whether we have solid, liquid, or gas, and then we obviously need to make sure we are balancing the equation. Okay. So hydrogen peroxide is catalyzed by the iodine ion to decompose into water and oxygen. So we have some new things, new ideas that we're playing around with. So let's begin to break this down. Before we go any further, though, let's think about what the word catalyze means. So catalyzed, okay, is another word for a catalyst. All right, a catalyst is a substance that speeds up the rate of a chemical reaction without, okay, undergoing any permanent change itself. All right, and so once I kind of write this out, it'll become more obvious what we mean by this. Okay, hydrogen peroxide is H2O2, and I believe that is a liquid. Okay, and then the iodine, okay, ion is an I negative ion, and we actually know that to be, okay, a solid. Okay, instead of writing it on the reactant side, the appropriate thing to do with a catalyst, right? I know that's a temptation, but the appropriate thing to do with a catalyst is actually to write the arrow for the reaction occurring and to put the catalyst over it, okay, right? To show that it is it is in fact acting as a catalyst. It is not going to be on either side of the equation. It's just going to help, okay, speed up or catalyze, all right, the reactants breaking down into the products in this decomposition reaction. Okay, we do know also, a little bit unique to this specific instance, is that we have water and oxygen, okay, being created, being produced. That's why we call them products, okay, from this decomposition reaction. So in this particular scenario, we would use the subscripts because we know water is H2O. Okay, that is how we write water, and we know that oxygen, being a diatomic molecule, has a 2 for a subscript. So this is one of those instances where, all right, I know I told you not to carry subscripts, but we are going to in this particular instance. And then we're gonna rewrite the equation. We're gonna balance the equation. Okay. I also failed to write liquid and then gas. Remember, do not forget our physical states. Okay. Again, and this helps us see it over and over. We put the catalyst, okay, over the reaction arrow. Okay. So, actually, all right. Thinking about minnow. All right, our acronym to help us balance the equation. Do we have any metals? Well, we do and we don't. We have a metal that's acting as a catalyst, so we're not going to count it when we're balancing the equation. That's an important kind of nuanced point that I wanted to make. All right. Do I have any polyatomic ions? Okay. We actually do not here. Even though these are compounds, these are not polyatomic ions for us to worry about. I know there's an iodine ion, but again, that is not on the reactant or product side. All right. It's a catalyst, so we are ignoring that. Okay. Let's continue. We then, consider non-metals that are not oxygen or hydrogen, except we don't have any. So we are going to focus, on the oxygens and then the hydrogens respectively. We're going to see if this is balanced. If it is, great. We're going to move on. So oxygen, we have 2 oxygens here. Hydrogen, we have 2 hydrogens here. Okay. We have 2 hydrogens here, and then we have 1, 2, 3 oxygens. All right. So what we're going to do strategically is we're going to focus on the oxygen because it's an odd number. And we're going to fix that odd number. And we're going to do that by putting a 2 in front of the H2O. That is going to give us, that is going to give us 4 oxygens, 2 oxygens in this water, and 2 oxygens in the diatomic molecule oxygen. And then we're going to have 4 hydrogens. All right. Now that we have 4 and 4, we're going to go back to the reactant side. All right. And we are going to put a 2 here. Suddenly, we have 4 hydrogens, much like the reactant side, or much like the product side. All right. And we have 4 oxygens. Awesome. That is now balanced. Okay, I'm going to pop out of here. I'm actually going to see how much battery I have left. I might need to pull an emergency audible. 17%. We got to plug this in. Okay, so you guys bear with me. Okay, bear with me. I'll be right back. Okay, I know that seemed basically instantaneous. It was quite an adventure that you did not have to participate in. You're welcome. Let's keep these annotations. They're so fantastic. Let's keep going. We're almost done, believe it or not. All right. Okay, we got a couple more to do. So what I'm going to do is I'm going to do the magnesium, bromide, and then in pairs I want you to work on the aluminum, trichloride, the aluminum chloride, pardon me, and then the decomposition of water. Okay, so let's get to it. Okay, we have a decomposition reaction of magnesium and diatomic bromine. We understand that it is going to split apart. Okay, we also need to write the states. And we know that this is going to be a gas. Okay, all right, so for decomposition of magnesium, bromide, we have, metals. Consider our metals first. We have 1 each. Those look good. Polyatomic ions, there are none. Non-metals that are not oxygen or hydrogen. Oh, look, bromine. Okay, we have bromine. There's 2. And bromine, we have 1 on this side. Remember, we're not going to carry the subscripts. Okay. All right, so we are going to put a 2 in front of that, bromine. And that looks to have effectively balanced the equation. All right. I want you to give these 2 a shot. All right, and then verify your answers using the internet and or a partner who's presumably smarter than you, because you should always pair with smart people. Okay, potassium iodide. Let's do this one. We have a K. We have an I. The I is a diatomic. You should know that. Okay, and it is. Oh, look, I made a mistake. What was the mistake I made? Pause it. Are we doing synthesis or decomposition? Decomposition. All right, so my excuse is it's very late. It's not a very good one, though. Okay. Again, potassium, that's going to be group 1. Okay. Iodine is also group 17. Since there are 2 of these, I believe we're going to need 2 potassiums. Okay, it's K2I2. This is going to be a solid. and it's going to decompose into its constituent parts, meaning, okay, we're going to have, okay, potassium. No? Reduce. Yeah. Oh, yeah, that's right. Sorry, I have an advisor here that carefully pointed out, all right, that, ladies and gentlemen, 2 divided by 2 is the same as having, okay, I, right? Again, it is late. It was a long day of travel, okay? And you get to see, right, the journey of a young teacher pioneering his craft. Okay. I got way too meta. I'm sorry. Oh, okay. Ki, decomposition. That's where we were. Onward. Okay. Here we go. Potassium. Okay. It's going to be a solid. Iodine. Okay. It's going to be a gas. All right. No. Gas. Iodine is solid at room temperature. I know things. Okay. Let's make sure that these are balanced. Looks like we have, okay, one of each on both sides. All right. This is good to go. All right. That was harrowing, but we did it. Okay. Let's try one more. And then I'm going to release you to page 15 of your homework, which you should have done, okay, by tomorrow, meaning the 7th. And we will know if you haven't done it, okay? You ever heard of Santa? Okay, he knows everything. He sees everything, all right? And Mr. Renard works closely with him, okay? So please get it done. Again, decomposition reaction, focus, Shanzer. Calcium hydroxide, okay? We know that calcium is a +2. We know that hydroxide, being a polyatomic ion, is a -1. So we're going to need 2 of those. All right. I remember that. All right. And then it's going to decompose into its constituent parts of calcium and hydroxide. All right. And we're going to remember our handy dandy acronym MINO. We're going to start with the metals, calcium. And balancing this equation, we have 1. This calcium, we have 1. On this reactant side, okay, we have 2 hydroxides, and on this reactant side, we have 1. We're going to take the odd man out, okay, this polyatomic ion that is alone, okay, and we're going to make him, all right, we're going to give him a coefficient of 2, all right, so this becomes a balanced equation. I hope that makes sense, guys. Please feel free to reach out to us. Even though we're going to be at training all day, we will try and get back to you with any clarifications or answers to questions you guys have. Please do complete page 15 for homework. Do the very, very best you can. The internet is a tool to help you after you put forth effort yourself. So we hope you have a great day, and we will see you tomorrow for the next edition of Magnolia High Advanced Chemistry Lecture Series. Good night, good morning, whatever it is.